Thanks for joining me. I'm going to go through this sheet fairly quickly. You're able to check your answers, hopefully get an explanation if you need one. Remember, the purpose of us doing this is that we have a CFA on Wednesday. So let's review. Number one, let's write electron configurations. Electron configurations. I need my periodic table here in front of me to help me out. F is kind of where we're going to be stopping. If we look on the periodic table, F is in the P block, it is in the 2P block, and it is in the fifth column. And so that's its ending. If we want to make sure we wrote the complete thing, we would need to write every full subshell up to that point. So if we saw a complete one, you would also see 1s2 written, and you would also see 2s2 written because those S shells would also be full. If fluorine turns into an ion, it gets a -1 charge, and that means it's going to be gaining an electron. And so everything would be the same, except 2p5 now becomes 2p6. This 2p6 means it's going to be kind of looking like neon because it would have a full shell. So when we get the electron configuration with an ion, it's going to end up with an ending of a noble gas. If we look at sulfur, which is element number 16. It's ending. It's also in the P block, but it's in the 3P block. It's in the fourth column of that block, so it ends up being 3P4. Now, if we wrote everything out, we would want to also say that it's 1s2, which is where helium is. There's also 2s2, which is where beryllium is. There is 2p6, which is where neon is. And there's also 3s2, which is where magnesium is. Just like with fluorine, if we do sulfur with a -2 charge, that means it has gained 2 electrons. Everything else is going to be exactly the same. The ending changes because now 3p4, there's 2 extra electrons. It's going to be 3p6. And again, notice what that is. That ends up showing us it's the same electron configuration that argon is in. All right, change colors. Part 2, N and O. These are both nonmetals, so they make covalent bonds. Potassium and fluorine, that's a metal and a nonmetal. They make ionic bonds. That's kind of what we're looking for there. Ratios. When we write formulas, ionic bonds anyway, they are in a ratio. That's what the little subscripts tell us. So the first one's asking us about K and F. Let's go through and check out our charges. K is +1, fluorine is -1. If we switch our ones, we end up with a 1-to-1 ratio because our formula would be KF. K and S, however, K is still +1, S is -2. If we swap those up, we get a 2, and so the ratio is now 2-to-1. So 2-to-1. Sodium and nitrogen. Again, sodium is also +1. Nitrogen is in, number 7 in group 15, so it's got a -3. So it would be, Na would be 3. We switch our numbers over here, and nitrogen would be a 1. So this is a 3-to-1 ratio with those. So again, all that we're looking for a ratio is how do these numbers compare to one another, 1-to-1, 1-to-2, and so forth. Our groups, number 1, these are our alkali metals. Group 2 are the alkaline earth metals. 17, I know this is really messy, but hopefully you're listening. Halogens, and then group 8A or 18, these are our noble gases. All right. All right, group 1 is 17, very reactive, has to do with their electrons. And group 1 only has 1 valence electron, so they want to lose them. Group 17 has 7 valence electrons, so close to 8. So again, both of these, they want to have 8 valence electrons in their outside shell. The elements in group 1 will lose that 1 electron, which means that their kind of next shell, if you want to think of it that way, inner shell, is full already. And then group 17 kind of does, I'll say the opposite, but they just need to add 1 electron to their outside shell to make sure that they're full. So don't need a whole lot of energy to be able to do that. What type of compound is made if we go from group 1 to group 17? That's going to be ionic. We would also have kind of a formula that looks like this. There'd be 1 of each because of +1, -1. If we had group 1 and group 16, this would also be ionic. It would look a little differently because group 1 would still be +1, group 16 would be -2. So the general form would be X2 with a Y. In other words, we need 2 of the metals and we need 1 of the nonmetals. And then finally, if element E and F combine to form EF2, so if F was in group 17, where would element E be? All right, so if it's in group 17, then it's going to have a charge of -1. If we did some backwards crisscrossing in order to get, hang on just a second. Apologies, quick commercial break there. So again, if we had EF2, and I know that F was in group 7 or 17, that means its charge would be -1, which means that kind of makes sense that if I crisscross, this 1 would end up here, which means the 2 would end up back over here. I'm looking for something that would be in the +2 charge, and that would be, well, that's not good. Hang on again. Apologies, I got signed out there. So again, what I was saying is that if I know that there's a 2 here, and I know this in group 17, I'm going to have -1. So if I switch those up, we're going to get that 1 there. All right, maybe I'll get through this without being interrupted one more time. Anyway, we do all this. E has to have a +2 charge, which means it is in group number 2. So that would be our beryllium magnesium group, alkaline earth metals. Moving on to 4, is it polar? Is it non-polar? Remember, polar means there's going to be an unequal distribution of charges. If we have an electron tug of war, someone is going to win. So number 1, bromine and bromine, no one's going to win. This will be non-polar. Number 2, notice the way that this is drawn. We got some minuses, we got some pluses. Sulfur is tug of warring on the hydrogens. These are both non-metals. Excuse me. Since they're both nonmetals, then we're going to probably get some unequal pulling. These indeed would be polar because we've got minuses and pluses. If we look at this picture right here with hydrogen and chlorine, again, nonmetal, nonmetal. We have 2 nonmetals. It's very likely that they're going to be polar. All right, so they're pulling in opposite directions. So this one would be polar. CH4 is a little tricky. We've got carbon in the middle and 4 hydrogens. Each of the bonds that are going to be in here, they're going to be polar bonds, but the whole molecule itself is very likely to be nonpolar because of the geometry of it. We didn't quite get into that, so it's okay. Number 5, nonpolar. Which one? Covalent bonds are shared equally, or they're going to be shared unequally? Well, if they're shared equally, they're nonpolar. And number 6, the bonds, the electrons are shared unequally. That's when we get polar. They're being pulled to one end, just like I mentioned yesterday in class about things being towards the poles of the Earth. Let's write some formulas real quick. All right, kind of one of the things I need to do as we go through these, we got to find our write our symbols and get our charges. I'm gonna make my ink a little smaller here. So strontium is FSR, fluoride is F, strontium is +2, fluorine is -1. Crisscross them up, and we should end up with an F2 at the end. Magnesium nitride, again, that's going to be just plain old nitrogen. Magnesium is +2. Nitrogen is -3. Switcheroo the charges, the 3 ends up over here, the 2 ends up there, and that one is done. Remember, don't include the pluses and minuses when we are finished. Sodium and phosphate. Sodium is on the periodic table. Phosphate, give me a moment. This is when we need to get our polyatomic table because this is not phosphide, this is phosphate. Need to look it up. Phosphate is PO4 and phosphate has a charge of -3. Sodium on our periodic table has a charge of +1. So let's crisscross our numbers. This 3 ends up over here with the sodium. The 1 ends up with the PO4, which we don't need to write. If we simplified it, we get Na3PO4. Gold, 2, that tells me the charge. Chlorine, -1 on a periodic table. Switch them up. The 2 ends up over here with the chlorine. The 1 ends up with the gold, which we don't write. And we are done with that one. Iron and sulfur. Iron is Fe. The 1 is a +1. Sulfur on my periodic table is an S. In fact, it is also under oxygen, so it's -2. switch up my charges. 2 ends up over here with the iron, 1 ends up with sulfur, which we don't need to write. And that would be my answer. Vanadium, IV. This is Roman numeral 4. I gotta find vanadium. Oh, it's just a V. All right, so vanadium's here, +4. Hydroxide, that is going to be one of our polyatomics. I need to look it up. Hydroxide is OH. It is a charge of -1. So there's my hydroxide. So I need to switch up my 4 and my 1. The 1 ends up over here with the V. The 4 ends up over here with the OH, which means I need to put parentheses after it. And my formula should be VOH4. And then we can start getting some covalent. Dinitrogen, that is 2 nitrogens. Tribromide, that is 3 bromines. And we're done here. Carbon, which is just 1, and tetrachloride, which is 4 chlorines. Those are nice and easy, aren't they? All right, let's name some things. Now, as we name, here's kind of the stickler. We got to make sure we're paying attention to the first one. Is it a metal? Is it a transition metal? Or is it a non-metal? Because we name things differently depending on who it is. So Na, in this case, regular metal. Sodium fluoride. Mg, regular metal. Magnesium chloride. Okay. Aluminum, regular metal. Aluminum. And then I need to look up NO3, which I believe is nitrate. Kind of come over here to your little chart because it's not going to find on the regular periodic table. NO3 is nitrate. So aluminum nitrate. Here we go. Change things up. Au is gold. Transition metal, which means it's going to have some parentheses to it. S is sulfur for sulfide. I need to figure out which gold I have. This is where we reverse crisscross. Sulfur's charge is -2. If you'll notice down the bottom, my ratio here is I've got one gold for 1 sulfur, which means my charges up here need to cancel each other out. If I'm going to kind of cancel out down the bottom, which means that gold would have to be a +2. +2 and -2 would result in no charges at the bottom. This +2 is what ends up in my parentheses in the Roman numerals. Same thing for the next one. Iron is a transition metal, needs parentheses, iron chloride. So which iron do I have? Well, if I use my periodic table, chlorine is -1. Since there's no numbers in the bottom, that means that -1 needs to be perfectly balanced out with a +1. And if I write +1 above iron, I need to put a 1 in parentheses. Excellent job. Ag, silver. That is also a transition metal and needs some parentheses. PO3, I believe, is phosphate. Let me double check so I don't make any mistakes. Oh, it's phosphite. Again, if it ends in ITE or ATE, it's usually going to be on the back of this chart. I need to know which silver we have. Got to be careful here. This is 1 phosphite ion. And notice there's only 1 of them. So I've got a 1-to-1 ratio. If I know what the phosphite charge is, looking on the periodic table, phosphite is -3. I'll give you a different color here. So phosphite is -3. That means that the silver would need to be +3 because +3 and -3 would result in a 1-to-1 ratio. So that would be silver 3. These last two are turning into covalent. And again, what I need to ask myself is this first term, is it a metal? Is it a transition metal, a non-metal? It is a non-metal. Since it is a non-metal, we need to name it with prefixes. This is carbon, but we've only got 1 carbon. We don't start off with a mono. So this is carbon. And there's 2 oxygens. That is dioxide. And then this is a non-metal. And I've got 5 nitrogens. So I've got pentanitrogen. And then the last name, I've got 7 oxygens. So the prefix for 7 is hepta. And then oxygen turns into oxide, and I don't think I've right heptaoxide. I think it's just heptoxide. Kind of drop the A right here. Pentanitrogen heptoxide. So with all these, make sure you're naming them properly based upon whether it's a metal, transition metal, or a non-metal. All right, let's wrap this thing up down here at the bottom on part 7. Label from a chemical bottle was lost and we get a green flame. Well, if there's a green flame, let's look at our little chart. Well, look at there. There's green, must be copper sulfate. Okay. The explanation for the different colors has to do with electrons kind of jumping from one energy level to another one. It says what state describes when an atom is at its lowest energy, its electrons are at the lowest energy. We call that the kind of ground state. And then when it gets some energy, like when we stick it into a fire, it goes into kind of an excited state. This is not doesn't want to be there. It requires a certain amount of energy to go from the ground state to the excited state. Eventually, it's going to return from the excited state to the ground state, and when that happens, that's when we're going to have some light emitted and given off. So generally, we're absorbing some heat right here to get it excited. When it returns back to where it's supposed to be, it loses that energy and we get some light. So we have emission. Emit usually means to give off. And we have absorption, which usually means obviously to gain or get something. So if we label these, you can see the way that this one is on the bottom. On the left, it looks like there's some energy coming in. It's going to cause the electron to jump. So this one, it's moving from the ground state to the excited state. And then it would be absorbing energy to be able to do that, right? So this is the one showing the electron gaining some energy. The reverse is happening on the other side over here. This is the side where it's kind of losing its energy. When it loses its energy, it doesn't disappear. This is when we have light given off. When the light is given off, this is emission. It is emitting colors, and the energy is going back out. It is when the excited state is returning to the ground. And our last question, when we see color coming off of this, it is because of the emission. It is not absorbing the energy, it is giving that energy back off. Hope you're able to get all of those. Give yourself a smiley face and have a good day.